Hey guys, Jason here again. We're back at the bench. Today we're going to have a look at the oscilloscope. In the last video I went through how I use a digital multimeter. Today we're going to go into the scope, right? So we're going to do the video in two parts, I think. Part one will be just some basic information about the oscilloscope, what it's used for, kind of how to use it, right? Part two, we're going to use our Mojotone JTM45 kit here, which was brought in for me to bring it to life. I've been just ironed out a few kinks in this thing, but it's working now. And we'll use this amp as a test case for how we use the scope to trace through a signal, right from the input of the amp all the way through to the speaker output. Stick around. So by way of introduction to the oscilloscope, I'll just go through the basic functions that I have on my scope here. So I bought this from a local electronics store in Australia. I'm sure the world over you can buy something very similar, if not the same. It's a two-channel oscilloscope, right? So you've got channel 1 and channel 2. What that means effectively is that you can have two different probes, right? So this is what our probe looks like. Okay, it's got an earth alligator clip, and it's got a hook here that allows you to hook it onto a signal wire in order to measure or to see on the oscilloscope what's going on. This scope came with two probes, right? So in theory I could actually have two different probes on here, and accordingly I'd have two different waveforms, right, coming up on the screen. Look, I've never used a second probe. I've thought about it, and I've thought about it in terms of, when we get to a phase inverter and the signal gets split into two, then hey, I've got the second probe there and I could actually have a look at both at the same time. I've never needed to. I just use it with one probe, it's all you need. This oscilloscope I find very handy because it has a built-in signal generator. Right, so you can see here I've got a BNC connector coming out of the front of the scope here, and it's connected to a 1/4" jack. I use this to generate a waveform, a sine wave, right, sinusoidal wave, and I can use this to inject a signal into the front of the amp, which I can then use the probe to trace through the amp circuitry. If your oscilloscope does not have a built-in signal generator, you need to get one, right? You need to have something that's going to generate a signal, ideally a sine wave, right? That's what you want to work with, a sine wave that you can feed into the input of your amp, the input jack, and then you can use the probe to trace through the circuit and confirm, I guess, that the signal is getting through correctly. And if it's not getting through, you've got a problem with your amp, you'll be able to use the probe to figure out where it is going wrong. Now, you can build amps without an oscilloscope, and I built many amps before I got this thing. But if you're really going to get into this kind of seriously, or with some with an amount of passion, right? This is amazing. My life on the bench here and building amps really changed when I got this thing, because I can diagnose faults, I can understand what's going on, I can really get into tuning, tuning an amp to this, the tone and the feel that I want. This is a really important tool for that. So let's talk about what this thing does, right? So on the screen here, what you've got is a center line. This is 0 volts, okay? And what we've got on the screen here is a graph of voltage over time. So the two main controls that you've got on the oscilloscope is volts per division, right? So you can see as I'm turning this dial, observe what's going on here. This is the voltage per square, right? So 1 volt per line on this graph, right? So it's volts on the y-axis and time on the x-axis. So you can crank this right up, right? So if you've got a really high, high voltage signal, you can go up to 100 volts per square on this scope. So whilst the voltage per division controls the scale, if you like, on the y-axis, so the voltage, over here we've got seconds per division. This controls, and you can see I'm changing it here. This controls kind of the scale of the time, because what we're doing here is we're measuring over a period of time the change in voltage. Okay, so at the moment this probe is just sitting on the bench, it's not connected to anything, right? So I'm just going to turn in the dials here just to try and explain what we're looking at here. For the scope, right, measuring DC voltage on an oscilloscope is pretty much a waste of time. DC voltage, you just use your digital multimeter. DC voltage on a scope just is a flat line, right? It'll move up depending on what your DC voltage is, or if you're negative voltage, it'll be below the line, but it'll be flat, right? So not that interesting. What you really want to use a scope for is to observe AC voltage, right? Because that's when you get the wave. Your guitar signal moves through the amp as an AC waveform. And the job of the amplifier is to take it from millivolts into volts that will actually move a speaker coil, and so you can actually hear it. Okay, so what we're going to do now is I am going to set up the signal generator. We will send in a sine wave into the front of the amp. It's about the same amplitude as a guitar signal would be, and then I'm going to show you the common kind of checkpoints, if you like, right, through the amplifier that you would use the oscilloscope to check that your signal is making its way through the preamp into the phase inverter, through the phase inverter into the power tubes, ultimately out into the speaker output. Okay, so let's do that now. Okay, so I've plugged in the 1/4 inch jack into the high input of the normal channel on this JTM45. This 1/4 inch jack and the coax is coming from the signal generator output on my oscilloscope here. So the first thing I need to do is turn on the signal, or set up the signal generator. So I do that by clicking this, and you can see my scope defaults to a sine wave. It's at 1 kilohertz and the amplitude is 2 volts. Now 2 volts is too high, right? Your guitar does not send out a 2 volt signal. So the first thing I always do is I click on this and I move the voltage of the signal to about 150 milliamps. Which kind of sounds low, right? But you think about your little passive pickups, they don't send out a massive signal. Something in that order. Maybe, depending on how hot your pickups are, you might get a little bit more than that, but that gives us enough to work with. All right, so 150 milliamps at 1 kilohertz. You can change the frequency, right? So unlike a guitar where you've got all sorts of frequencies that are coming through the amp, the signal generator will only send a single signal through. But for testing purposes, that's actually quite useful because it makes it a lot easier to read what's going on. So once that's up, so now that's set up, I go back to the examining what's happening at the probe level. And at the moment, my probe is not connected to anything. Okay, so now I need to connect my probe. All right, so what I'm going to do is I'm going to connect this ground clip to the ground on the speaker, the input jack here. So nice convenient ground location right there. And I'm going to connect the probe to this point here in the amp, which is the 268K resistors, right? So in reference to the schematic and the layout diagram, which I'll show on the screen now, these are the 268K resistors coming from the high and low inputs of the normal channel, and I've connected the probe on the other side of those two 68k resistors, which is basically the grid of V1A. Okay, so I've now got the generator, the signal generator is now turned on. So there you go, it was on, I just checked it, it's turned on. And what I need to do now is I need to get the scope in range so that I can actually see what's going on here. So you can do this manually, as what I'm doing now, right? You can see, here's my, the other way, here's my sine wave that's now hitting the front of the amp. Well, you know, it's going into the grid of V1A. My scope actually has an auto set function over here. So if I click this, it just does a best fit. And there we go. Okay, so if I click measure, my scope's got a measure function as well. And it's telling me that I've got a 320 millivolt peak to peak sine wave, and you can see the period here, it's 1 millisecond, or frequency 1 kilohertz. So, you know, at that point in the amp, I can see that our test signal is coming through nice and clean. Look at it, you know, it's a very nice sine wave. There's no distortion on that wave. It's what we'd hope to see. Okay, so the next thing we want to check is that the first triode in the amp, so V1A here, remember this green wire here, we've just checked the signal here. The green wire goes into the grid of the first gain stage in this amp, V1A. And its job is to amplify that signal, right? Which it does so through, it comes off the plate here. This coupling cap right here is the first coupling cap. So if I measure the signal on this side of the coupling cap, I should have an amplified signal. On this side, I have an amplified signal as well, but I also have that amplified signal sitting at probably 200 odd volts DC, okay, because it's still connected directly to the plate of the tube, and the plate is where you got your high voltage, right? The job of the coupling cap is to allow your guitar signal to pass. Imagine it passes through it, but it leaves the DC on this side, and over here there's no DC voltage, just the AC. So let me connect my probe to that side, and you can see it's off the scale. So let me move the voltage divider here. I've now got, and you can see I've moved this to 5 volts per square. I've now got nearly 20 volts peak to peak, right? So we went in one gain stage, we went from, you know, what was 320 millivolts, right, to 19 volts peak to peak. So, you know, that's just one triode in your amp, guys. You know, these things, these tube stages can really amplify your signal. So, you know, that's why tubes are better than pedals. Okay, so let's move the probe along in the circuit. So we're at the first, after the first coupling cap here on the normal channel. If we move to the volume on the normal channel, you can see the input to the pot. It's the same as you'd expect, right? Because, you know, they're connected after all. You'd expect it to be the same. Let's move to the wiper of the normal channel. So this is registering nothing because the volume is on 0. If I turn the volume up, you can see, just move the scope. Here's our signal, right? To our pot. You can see, moving the volume up and down, I'm getting what I'd expect to get, which is I'm changing the amplitude of my signal here with my volume. Okay, just what you'd expect. So that's 0 there. Now you know how loud a JTM 45 is. I've measured the output the RMS clean output on this amp. It's 53 watts clean power, right? It's a loud amp, right? You put that into a 4x12, crank it, it's loud. So that's 0. It's kind of 1, 2, 3 or 4 there. 4 on the volume, 4 on the volume on a plexi. Even the JTM 45, it's pretty loud, right? So we've got a decent amount of signal there. I don't need to crank the amp too hard for this test. Right, so back to 0 there, bring it up a bit. Here we go, we've got some signal coming through. That's fine to test the rest of it. Right, so in the JTM 45, or the 1959, 1987 plexi, quite similar. These things come into different sides of these mixed resistors here. In the JTM 45, these are 270k. 270k this side, 270k on the bright channel, and the bright channel has the bypass cap on it as well. Right? And these things come together and then head into V2A, this side of the V2. So the next thing to check, right, we've checked that we've got nice signal coming off the wiper. We want to check on this side of these mixed resistors. Right, so just tracing the signal through the circuit. Right, let's play with the volume. That all looks pretty good. Sine wave's nice and clean. There's no obvious distortion on that. So far so good, right? We've only been through one gain stage here, remember? Because the old JTM 45s, they're not cascading V1A, V1B. Now this signal moves into the grid, right, of V2A, and here we're getting into this V2A gain stage feeding the cathode follower, which is V2B. So a little bit more complicated to measure here, because you can't get access to a DC free voltage, right? So you want to measure AC here, but the AC is riding on top of DC. So what we can do though is I can attach this probe to the plate of V2A, which is actually sitting up at, I can't remember the voltage here guys, but it's something like 200 volts, right? Somewhere around there, DC. And you can see it's not even on the scale here. Now, if I move the position of this, I can kind of try and get the line on the scope, but it's not what you do, right? What you do is your scope will have, if you click on the channel button, you've got this thing called coupling up here, okay? And this allows you to set what the probe will examine or filter out, to use another way to think of it, right? So it's DC coupling at the moment, which means I'm going to get, the probe is going to look at DC, it'll look at AC as well. But if I move this to AC, look what happens. All right, it filters the DC out. I move the position back as I played around with the position here, move it back to centered. Okay, there's a center line there. And because I'm just doing AC coupling, this is an important thing to know. I've got rid of the DC out of my out of the wire, and I'm just looking at the AC signal, right? So it's nice and centered for me because it's just eliminating the DC, which is really cool. So let me click measure. I've got 22 volts here, right? So remember, I had 22 volts coming into the input of the normal pot, but I've got the volume turned quite a long way down through the mixed resistors. It's getting amplified again by this gain stage, and it's 22 volts after V2A has had its way with the signal. If I move this volume pot up, you can see, right? Remember I had 22 maximum coming out of the first gain stage. If I move the volume up, you can see I've got crap loads. This is where you get gain in the amp, right? Alright, so moving on to V2B, this is our cathode follower, which coming off the cathode of V2B, we've got the 100k resistor to ground, and then we're feeding directly off that, on the top of that 100k, the tone stack. Okay, so I'm going to connect the probe directly to the other side of this treble pot capacitor. Okay, so I've now got the probe back in just normal, DC coupling mode, and if I connect this probe to here, we can see the signal is, let me put it into measure. Here's our volume. Right, so we're now on the tone stack side of that capacitor. Now, you'll notice straight away, right, that the voltage here is lower. But what we've done here is we've moved, the cathode follower is changing the signal from a high impedance signal to a low impedance signal. Why is that important? Well, it's important because a low impedance signal can drive through a set of passive components and minimize signal loss. So same way an effects loop works, right? Your effects loop, the send part of an effects loop, the job of the send is to convert your signal to a low impedance signal so that it can go out across, what could be 20 foot of cable to your effect pedal, your delay or whatever, and then all the way back again, 40 feet of cable, and have no signal loss, or no audible signal loss. The same thing with the tone stack, right? The job of the cathode follower is to set up a signal that can move through all of the treble, middle and bass pots, which is they're all passive, right? All they do is cut signal. And by doing this, what we're doing is setting up a signal that can drive through that passive network and not experience too much signal loss. Right, so from here, now I can see that we've got a signal that's going okay, coming through to the tone stack. This hits the input of the treble pot, which is right here, and you can see it's the same signal, right? It works its way through this network, and it always comes out on the treble wiper. All right, that's the output of the tone stack, so I always check the treble wiper. So if I'm getting the signal here on the middle lug of the treble pot, so far so good, right? Because from here we go straight into the phase inverter, tube. And if we get into the phase inverter tube, then it means that the preamp, right, is all good. All happy days here. Okay, the input to the phase inverter is here. I'll show it on the schematic. Right, and you can see my signal is still all good at that point. So we're all happy there. And we're now basically into the power amp, right? So the phase inverter is actually, even though it's a preamp tube, we call it the part of the power amp because its job is to divide the signal into two equal but opposite phase signals to drive your push-pull power section. Okay, so moving along from the phase inverter, I'm just going to go straight to the output now. You can actually use your probe, on the power tubes, maybe looking at the grid, the input signal to the grid. I'd only ever do that if I find that there's, some issue between the phase inverter and the output. It's pretty rare, right? Most 90% of your issues are going to be somewhere in the preamp, I would suggest. Can happen, right? But let's just go straight to the output, and I'm just setting this onto the 8 ohm tap on the impedance selector. I would often just connect this to the speaker output, right? But the way this amp has been built, it's not really a convenient spot for it. So I've got it on the 8 ohm tap anyway, which is fine. And the volume is on 0, so I'll just bring the volume up a bit here. And you can see what I've got here, 10 volt peak to peak signal. Now, one of the observations again you might make as well, where I had this, massive voltage in the preamp, how come it's so small when I get to the speaker output? And I've got the volume there, so that's 0. It's probably about 1, 2, it's probably about, it might be 2.5, which would be pretty loud, right? That's loud. You put that into a 4x12. I mean, look, loud is relative, right? But a 50 watt amp on 2.5 to 3 on the master volume, you kind of get the idea, right? It's not quiet. So why is the voltage so low? It's because, again, this is a different impedance signal, right? This is driving an 8 ohm load, so it's got massive current. This is the difference, right? The voltage is lower, but the current is very high. Well, the available current is very high at this point in the amp. What I'll do is I just want to take you through a very easy way to measure the power that you're getting, right? If you're measuring the voltage at the speaker output into a resistive load, right? So part 1 of the video, I showed quickly, the resistive load that I use on the bench here. You've got to use a resistive load, not a reactive load, not a speaker. It's got to be a resistive load to do this measurement. But we can take this measurement here, 10 volts, and we can easily do a quick calculation to show the actual power in watts. All right, how many watts, clean watts, is this amp putting out at this point in the volume? And if I move this down a bit, so at 20 volts peak to peak, let's do the calculation on screen now. And at 30 volts peak to peak, let's do the calculation on screen. And so on and so forth, right? So, cranking that volume right up until the sine wave starts to square off, that's where your peak power is. This amp I measured 53 watts, okay, before the sine wave starts to, clip, basically. And at that point, you're getting the power section is moving into, into distortion, into clipping. So you're just going to back it off a bit from there, and that's your measured clean output power. Okay guys, I hope this oscilloscope video was useful. If you've got one and it's kind of sitting on your bench and you didn't really know what to do with it, hopefully this has been helpful. If you've been thinking about getting one, look, if you're going to be building a few amps, I'd recommend it. If you're just going to do 1 or 2, whatever, right? Get your digital multimeter. It's all you're really going to need. You'll be able to kind of get through with one of these. But if you're serious about, progressing with your journey, really learning about amps, getting to the point where you can kind of troubleshoot, some more serious problems, and get into kind of, tuning and understanding more about what's going on in one of these things, I recommend it. This particular Mojotone JTM45, the guy that brought it in, Nigel, he wants me to hang on to it, and we're going to do some mods on it, which is kind of, what I do, right? So, JTM45, that's cool. It's a cool amp. Yeah, no worries, right? But he would love to take it into something perhaps a bit more modern. This is a really good platform to do a Dirty Shirley clone. It is JTM45 base, which is the Dirty Shirley is. It's also EL34. It's a Plexi 50 watt output transformer on this Mojotone kit. The Dirty Shirley, even though it's 5881 power tubes, it's a 50 watt Plexi output transformer on the Dirty Shirley, right? It's not a JTM45 power transformer, which is normally 6.6K to 8K primary on a classic JTM45. This is more like 3.6K primary on the Plexi 50 watt output transformer. So it's pretty similar output transformer wise and output setup to the Dirty Shirley, and these boards, this preamp section, can be converted into a Dirty Shirley relatively easily. So if that's of interest to the channel, please post some comments below. Look, if there's enough interest in it, I will document the mods to one of these to take it into Dirty Shirley, and I will post a video on that. Let me know, guys. I'll catch you later.